Now, much like Chapter 8, and thinking about things that we've done in Orgo 1 with alkenes, we can also do electrophilic addition reactions to alkynes. And one of the first ones we're going to look at is going to be a hydrogenation. Our hydrogenation is going to be adding hydrogens to your alkyne to reduce it down. And this behaves the exact same as what we see with alkenes. So if you have a triple bond and you use hydrogen gas with a metal like nickel or platinum or palladium as your catalyst, that will reduce you all the way down to a alkane. We are not going to be drawing mechanisms for a lot of these, but to kind of think about how this works, this is going to kind of behave almost like a UFO coming down to like abduct a cow. If I was better at drawing, I actually might have made that the scheme instead of this one here. But your alkyne will come and it will coordinate to your surface, and this is why you need like a metal, like a nickel or a palladium or a platinum. That surface is covered with a bunch of hydrogens, and they will now be in close proximity, so then you will get an addition. Normally, in the case of your alkene, it's now fully saturated and then gets kicked out. In this case, what will happen is it just adds another one and then eventually gets kicked out. So first thing is, if you have a triple bond, H2 and a metal, boom, all the way down to a alkane, single bond. Now, what happens if you don't want to go all the way down to a alkane, and instead you actually want to go down to a double bond? Well, I have the reaction for you. Actually, there's two. So there are two possible ways in which you can do a partial reduction. So going from a triple bond down to a double bond. The very first one is using a Lindlar catalyst. A Lindlar catalyst is very similar to the catalyst that we see in the full hydrogenation. However, we poison or we weaken that catalyst by the choice of something else. There's a bunch of different versions of Lindlar. Barium sulfate, quinoline, a calcium carbonate, a lead acetate. Any of these can work. In general, if you just write Lindlar, it just means one of them. And in here, because of the fact that that palladium catalyst or that nickel catalyst, palladium, most of the time Lindlar is going to be palladium, but that metal that you use is going to be poisoned and it's not going to be able to go all the way down. So instead, it's just going to do a syn addition of just one. Now, if you don't want that syn addition, which is going to give you your cis or Z, if we're thinking of E and Z, stereochemistry about our double bond, we can use a slightly different mixture, and this is actually going to be a very different type of reaction. This is actually going to be radical chemistry. Again, mechanism here we're not going to draw, but we can use metal, most common one being sodium with ammonia. So NaNH3 is the most common example that you'll see. And this will actually do a radical reaction that will give you an anti-addition, forming a trans or an E-type double bond. In terms of reactions, this is actually a really cool reaction. The sodium metal, when it's solvated by your ammonia liquid, is actually a beautiful blue. And it's a really kind of cool reaction to physically look at. If you want to go all the way down more, you can actually do multiple equivalencies, because this isn't like poison like we see like in the Lindlar. So to kind of like put all of these kind of like in context, let's consider a generic triple bond, and then let's react that with all of our different conditions. So we have to our right our H2 and platinum, to the bottom H2 and our poison platinum, which is our Lindlar, or to our left our sodium and our ammonia. Each of those will give us a different product, and these are going to be the three main types of reaction conditions in which we are going to consider. So the first one, and the probably easiest one, is going to be our H2 and palladium. This is going to be a full reduction, meaning we're going to go all the way down to our alkane. So if I count my number of carbons, 1, 2, 3, 4, 5, 6, 7. So this is going to go all the way down just to our 7 carbons all just in a row. 1, 2, 3, 4, 5, 6, 7. So here is just our kind of like base structure with no types of bonds or anything whatsoever. So that's our full reduction. Our partial reductions are going to be our other two. So our syn addition is going to be with our Lindlar, because this is still going to come down like a UFO and like go to try to abduct the cow, which are our hydrogens. So in terms of our product, we're only going to get to a double bond, but it's going to be on the same side. So our hydrogens are going to be both at the bottom, and then the rest of my carbon stuff will be up on top. So that just gives me my 4 carbons. So I got to draw my other 3 in, and you'll have something like this. Overall, in terms of our stereochemistry, my big groups are both in the top, meaning we would call this Z for Zaimside or Zusammen. Or if you wanted to just be simple, we could say cis, because they're on the same side. The other option is going to be using our metal ammonia. This is going to be a radical reaction that's going to do an anti-addition. And that anti-addition is going to reduce our triple bond down to a double bond. And that's going to give us our opposite stereochemistry. So if we wanted to draw enough, 1, 2, 3, 4, 5, 6, 7, yeah. A structure that looks like this, where we put hydrogen on one side and then hydrogen on the opposite. This would have our E stereochemistry, or be known as trans or opposite. So these are our 3 major types of reduction reactions that we can see. H2 and platinum, full reduction. H2 and Lindlar is going to be a syn, meaning we're going to go down to our Z stereochemistry, where our metal ammonia will go down to our E. Now, I do want to give a kind of quick kind of like mention that metal ammonia looks a lot like our sodium amide, and those are actually 2 totally different things that we both see really common in our triple bond. So both of them have a Na and then some NH stuff. Our Na separate NH3, meaning our metal and ammonia, but we'll often write just kind of with a dash between, is all about breaking our alkynes. This is a reducing agent, and it will do a single hydrogenation, giving us a trans product, which is going to be our double bond. On the opposite side, if we use sodium amide, NaNH2, this is a single molecule, not 2 separate. This is going to go and help us form alkynes. This is going to be a really strong base. And this also, when we think about a geminal dihalide, this is going to give us an alkyne on our terminal side. And we can also use this with a alkyne when we're trying to do a reaction like an SN2. So if you have a triple bond and you are trying to do an SN2 and you use your sodium amide, that makes that a nucleophile and come and attack. If you instead accidentally add metal ammonia, that's not going to serve as a good nucleophile. Instead, you're going to get a reduction. So I really want to point out that those 2 are different. Those are not the same. One is a reducing agent. One is a base, which is going to help make a good nucleophile for us. So that's our kind of like summary of different ways in which we can go through and reduce a triple bond down to a double or a single.